considering we had a lot of problems on the Zoom and my internet kept going in and out. So I have decided to record the whole lecture and put it up on the WebCT thing so everybody has access to it. I'm going to start off where we left off from on Wednesday. So where we left off, we were talking about solvents and solutes and pH levels. A solution is a homogeneous mixture. That means every section of it, every part of it is exactly the same. So you have a solute is something that you dissolve. So if you had salt water, salt would be solute and water is the solvent. Water is considered to be a universal solvent because it can dissolve everything that is ionic and everything that is polar covalent. Oops. Polar covalent bonds. So, and these are called aqueous solutions. We talked about molarity, which is moles over liters. Liters of solution. So let's try to do one like a simple math problem. So if I had NaCl, if I had 25 grams of NaCl dissolved in 100 ml of water, one mole of NaCl. How do I find the mole of NaCl? I would look on the periodic table, and Na is 23, the atomic mass is 23, and Cl is 35. This is grams per mole. Grams per mole. So that's 58 grams per mole. That means 1 mole of NaCl is going to be 58 grams. I have 25 grams. So that is 25 divided by 58 will tell me how many moles I have. Let me take out the calculator. I don't want to do that. Just give me a second. 25 divided by 58 is 0.43 moles. I have 0.43 moles. I have 100 ml of water, which is 0.1 liters. Divided by 0.1 is the molarity of this is going to be equal. The molarity here is 4.3. Right? 4.3 moles. The molarity is moles per liter. Moles per liter. This would be the molarity. You need to, for your test, you need to know how to calculate the molarity. You'll have a couple of questions on that, so please know how to calculate the molarity. when we talk about solutions, another thing that we have to know, certain products are hydrophobic and some products are hydrophilic. The word hydrophobic means that they are, they tend to be water, oh gosh, this thing keeps jumping up all over me. The word hydrophobic just means that it is entirely afraid of water. So if you had a molecule of water and think about another molecule of like oil or stuff like that, they don't like break up into the ions, and they don't solvate, they do not dissolve. That would be hydrophobic. Hydrophilic molecules, on the other hand, are everything that's ionic and everything that is polar covalent. Hydrophobic is going to be non-polar covalent. Most biochemical reactions in your body are going to use water as the main source of transporting things from point A to point B. Things are dissolved in water and then they're transported. So everything is an aqueous solution. Whatever is dissolved is the solute, and water happens to be the solvent. The next thing we were talking about was pH. pH of water is 7. pH is the potential of hydrogen. The more H plus they have, the more acidic it is. The more OH minus it has, the more basic it gets. OH minus would be basic. So if I look at the pH scale, it is hydronium ion is just, let's look at the pH scale. Anything up to this is going to have a higher concentration of H plus ions than OH minus ions. Anything barring the 7, the 7 is going to be H plus is equal to OH minus ions. And everything from here on down, the OH minus ions are greater than H plus ions. Everything up here, because the H plus ions is greater, are called acids. Everything in this zone are called bases. Water is very unique in this situation because water is both an acid and a base. If I take H2O and I break it up, I would get H plus, equal concentrations of H plus and OH minus. A hydrogen ion and a hydroxide. We also talked a little bit about buffers on Wednesday's class. In order to understand a buffer, you have to understand that water, when it breaks down, it produces both OH and OH minus. So depending on where homeostatically, what is homeostatically required to bring back your blood. Let's take blood as an example. To bring your blood back to 7.4. So let's say for some reason it has become more acidic, OH is released. If it becomes more acidic, then you release OH, which will then absorb, OH minus will absorb the H pluses, make both of these together will make water, which is neutral. So, and then it brings the pH back down. If your blood has a lot of OH ions, if it has a lot of OH ions, then the idea is to release H plus, and both of them together will make H2O, and the pH goes back to 7.4. everything that we did in this chapter. We talked about water being a polar covalent bond. Between the partially negative and the partially positive, there is a hydrogen bond. The hydrogen bonds are actually responsible for most of the functions of water. The fact that water is adhesive, water is cohesive, it has a very high boiling point, it has a higher melting point also compared to other things. The fact that it has surface tension, it has evaporative cooling, it produces, all of these come from the existence of hydrogen bonds. Water is also considered to be the universal solvent, because it can dissolve all the substances that are ionic as well as all the substances that are polar covalent. Water has a pH. The more H plus ions there are, the more acidic it is. The more OH ions there are, the more basic it is. Water, on the other hand, is H plus is equal to OH minus. We also learned how to do molarity, moles over liter. That is, molarity in very general terms is just concentration. How much concentration of X is in water. That completes 3. I'm going to be starting chapter 4, which is basically understanding how carbon works. We are a carbon-based organism, and this chapter kind of talks about the chemical structure of carbon that allows it to form so many different bonds and so many different classes of compounds. This is one of those chapters that kind of forms the crux of everything that you're going to be doing in this class. So please pay attention to how carbon forms bonds, the different functional groups that it has, because the functional groups are what give it an ability to perform different functions. So it is, read your textbook. After the chapter is done, please read your textbook. If you have questions on how the things work in that, please make sure that you email me. So let's look at the structure of carbon in this chapter. Although, if you think about the 4 major macromolecules in your body, they are proteins, which are basically some form of carbon, hydrogen, oxygen, there's some nitrogen there, there's some of them have, and they have sulfur, and there are other minute amount of things, sulfur. DNA basically is carbon, hydrogen, nitrogen, and phosphorus. Carbohydrates is CHO. And then you have lipids, which are other lipids, which is another major class of molecules in your body, which are made up of CHO and some N. There's some N in certain types of lipids, but essentially CHO. So you will notice that we are organic molecules. Organic molecules are basically carbon-based molecules. Most of biology is dealing with organic molecules. We are going to look at what makes carbon so special that it is able to do all of these things. And most organic molecules have carbon. They're carbon based, so there's a colossal chain of carbon, and there are other things attached to it. Organic chemistry does not include, while CO2 is carbon based, it is not a part of what we will be learning. So let's look at some of you have done some chemistry. So carbon has basically 6 electrons, and the way they're organized is 1s2, 2s2, traditionally this is what it would be if you just followed your simple electron configuration on your periodic table. However, carbon is able to kind of, it forms this hybridized orbitals. Instead of being S and P, it's actually sp. So there's sp1, sp2, sp3. So you will have, instead of doing, so it does, for this class purposes, you will learn more in your organic chemistry class. It is 2s1 and 2p3. So what does that mean? What does it allow it to do? It allows it, so I'm just representing each orbital as a box. If they were all 4 boxes, I would have an electron, 1 electron. Each box can hold 2 electrons. Each orbital can hold 2 electrons. However, it's equitably distributed, having 1 electron in each box. So this is the exception. Oops. This is what your general rule would be, and carbon does sp hybridization, and that's why it forms this one, which is a sp hybridization. You know the spelling. Hybridization. It's able to form 4 bonds that are equitably distributed, which is what gives it its stability, which is what allows it to form so many different structures, allows it to bond with itself. Many things bond with itself that are diatomic molecules, bond with itself multiple times and create different structures that makes life possible. They are tetravalents, meaning 4 valence electrons. They have 4 valence electrons. If I was to draw carbon in the Lewis structure, it would be 1 electron, 2, 3, 4. 4 electrons. Carbon can form single bonds, double bonds, triple bonds. We have to know, before we go into anything with organic chemistry, we have to figure out what the prefixes for everything is. So if I have one carbon, which is like as in CH4, the prefix would be meth. If I have 2 carbons, the prefix is eth. 3 carbons is prop. 4 is but. 5 is penta. 6 is hexa. Hepta for 7. Octa for 8. Nona for 9. And 10 is deca. So we're going to start with the first main group, that is for carbons. They can form a long chain of carbons, can form like a long chain of molecules. The first one we're going to look at is the first one we're going to look at is an alkane. Alkanes are when they have at least one alkane. Alkane is they all have all single bonds. Every carbon is single bonded. So I would go this way, just single bonds with hydrogens all over the place, because they have to form 4 bonds, so they have hydrogens everywhere. The generic formula for this is CnH2n plus 2. So if I have 6 carbons, all single bonded to each other, then I would call it hexa for the fact that it is 6 carbons, and ANE from here to indicate that it has all single bonds. So if I see the name hexane, I know that there are 6 carbons and they are all single bonded to each other. So they are, it is an alkane. So that forms the basic structure of molecules. The next one we have is, they do have branching. I'm not going to expect you to name them, but you do need to know. So the next one we have is an alkene. Alkenes just means that it has at least one double bond. And so in this case, I have 4 carbons. There is a double bond. I would start numbering them from here. You want to give the double bond the lowest priority. So you're gonna start from here rather than calling it from this direction. So it will be 1-butene. You must specify where the double bond is. But comes from the fact that there's 4 carbons. Ene comes from the fact that it is an alkene. There's at least 1 double bond. And this number here tells you where that double bond is. So in this case, it is 2-alkene, because it's in the second one. If the bond was here, if this was the bond, then I would name it, then it would be 1-butene and not 3, because you must give it the lowest priority. Why doesn't it go back? Okay. So this one would be, if the bond was here, it's 1-butene. If the bond was here, it's still 1-butene. You just have to flip the molecule around so it gives you the same numbering. The next one that is going to come up a lot in this class when we look at glucose, when we do cellular respiration and photosynthesis, is cyclohexene, cyclo molecules. These guys have the same configuration, same generic formula as alkanes. H2N. So alkane is CnH2n plus 2, and alkene is CnH2n. And then the cycloalkenes. So an alkane, so I'll write it here, cycloalkane. Also has the same formula, generic formula as an alkene. So when you flip it and make it into a circle, then you're going to get the exact same formula, same number of carbons, double the number of hydrogens for the number of carbons as an alkene. Benzene molecule, benzene molecule is a very important molecule in as we go along. We're going to use the benzene structure would be the same, but then there are many attachments that happen. Instead of hydrogen, you would have other attachments to make it different molecules that we use biologically. The next type of hydrocarbon we have is an alkyne. Alkynes have the generic formula of 8CnH2n minus 2. Again, you'll follow the same thing. So if I had 3, let's say I have 4 carbons, and this one has a triple bond, so it would be but, YNE. And because it is in the first carbon, it would be 1-butene. So just to recap everything that we did in terms of hydrocarbons, the first class is alkane, that has the generic formula of CnH2n plus 2, and you would use the prefix of meth. You count the number of carbons and you use meth at, or depending on the number of them, you'd use that prefix. And the last three alphabets, there would be A and E. So if you have 4 carbons, it would be butane. The next one is alkene. Alkene's generic formula is CnH2n, and that would be, if it was, let's say the double bond was in the second carbon, then you would go 2-butene, E-N-E, from the alkene. The next one is an alkyne that has at least 1 triple bond. A triple bond is going to, the generic formula is CN, H2N minus 2. So if it was 4 carbons, and if the triple bond was in the first, around the first carbon, then it would be 1-butyne, YNE, from the alkene. The another class of hydrocarbons are cyclohydrocarbons, where it kind of forms a ring. If it forms a ring, then it has the same generic formula as the alkene. And so if you had a hexane, hexane would be C6H14, because it's 2N plus 2. But if it was a cyclohexane, then it would be H6C12. Carbon has this amazing ability of making various types of isomers. So do other carbons, but in this compounds. But in this case, we're going to talk about carbons. The first one is a structural isomer. Structural isomer is where the formula that you write is going to be the same, but the structure of the form is different. For example, if I did C6H12, this can be drawn out as either a alkene with a double bond in the first carbon. That way you don't have to mention it. Or it can be drawn as a cyclohexane. So I could have a hexene or a cyclohexane, and they would both have the same formula, but the arrangement of the molecules would be different. So the molecular structure of it would be different. And that is the first example of an isomer. The next one that we have isomers are cis and trans isomers. So the structural formula is a cis and trans isomers. Carbon is capable of attaching with different things, and you usually, when you name them, you have to give them priority. So let's assume that this X is fluorine and this X is chlorine. Both of these have a larger atomic number and atomic mass than hydrogen. So you would go, and this one is the highest, so you would go 1, 2, 3, and 4. It doesn't matter, 3 and 4. If the high priority ones are on the same side, then they are called a cis molecule. If they are on the opposite sides, so if I had this one as fluorine and this one as chlorine, then I would go 1, that would be 2, 3, and 4. So since the higher priorities are on opposite sides, they are called trans. So trans molecules usually are at a lower energy level than a cis molecule. So if you think about your eyes or any other, or photosynthesis, basic photosynthesis, where light is absorbed, the energy in the light is absorbed, a particle of light, photon is a particle of light. A particle of light, photon, is absorbed by a trans molecule, and then it flips and becomes a cis molecule, drops down, and energy is released, and you're able to do work. The next type of isomer we have is an enantiomer. Enantiomers are going to need a chiral carbons. These carbons have to be chiral. A chiral carbon. A chiral carbon is basically that it has, the carbon is attached to 4 different molecules, X, Y, A, and B. None of these things can be the same. If they are the same, then the carbon compound is called an achiral carbon. So a good way to think about it is think about your hands. You cannot superimpose your hands on one another. If you superimpose your hands, your thumb and your pinky will be sticking in, your thumbs would stick in opposite directions, right? You can mirror them, but you cannot superimpose them. And this changes the functionality of it, and how it reacts is changed because of what the accessibility of the molecules are. Remember, these are kind of large molecules, so if you want to react with something, you need access to it. So chiral molecules will have different types of accessibility. Your amino acids are all based on this. Glucose is based on it. All of your amino acids are based on this. For example, your body prefers L isomers to D isomers. It's just the way accessibility and receptors in your system work. Structural isomers, because hydrocarbons are capable of making branching off. So it can, the formula for this is going to be C5 H12. That's basically the formula for both of them, but the way they are structured is different. The longest chain here is 1, 2, 3, 4 is a butane, so you go with the longest chain. So the name is going to be bute for the longest chain, and they're all single bonded, hence ane. And then there is a branched chain here, which is 1 carbon, hence meth, and YLE signifies that it is a branched chain, and it is connected. You have to always give the functional group that is attached to it, or anything else that is attached to it, the lowest priority possible. So I would start numbering them from here: 1, 2, and 3, and 4. So it would be 2-methyl butane. Both of these are, however, when you're writing the formula out, both of them would be written as C12, C5H12. Here is a good example for cis and trans, which we talked about, chiral enantiomers. Enantiomers are one of the most important things that we will be talking about later on, especially if you guys go forward and get into pharmacology. Enantiomers, drugs, are based on the orientation. Is it a L or an D? And how they react with your body, how it is even absorbed in your body, and even if your body accepts it, depends on the L and D structures. These structures, how just changing this structure for ibuprofen, S and R are basically the same thing. It's S and R tells you the structure of S and R is just an orientation of where the largest functional group or the largest group of molecules are, like we did for chlorine and we did for fluorine. It just tells you in which direction is it going clockwise or is it going counterclockwise. Luckily, you don't have to do it in this class, but you will have to do that in your organic chemistry class. So we talked about the basic skeleton. The basic skeleton can be an alkane, alkene, or an alkyne. However, what they do in your body, are they soluble in water? Are they insoluble in water? Do they act acidic? Do they act basic? What type of covalent bonds or what type of hydrogen bonds do they form with one another? Their functionality comes from whatever is attached to it. There are various functional groups attached to it. So something that everybody is aware of is alcohol. If I do this, 2 carbons with an OH group attached to it, then it is ethanol. Alcohol that goes in your gas tanks, alcohol that is later on processed and you can drink. However, the same thing if I had this, is an isopropanol. Isopropanol is rubbing alcohol. And both of these have very different functionalities from this, which is ethane. These two do not function like one another. And this is also different from this. So ethanol is very different from ethane, and isopropanol is very different from propane. And the reason being, their functionalities are that functionality, how it functions and how it behaves, what makes rubbing alcohol and propane different from one another is the existence of this group, the OH group. Those groups are called functional groups. So we're going to look at a couple of functional groups and how they change the functionality of what your basic hydrocarbon would do. There are basically 7 functional groups. The first one is a hydroxyl group, which is attachment of an OH. Then you have the carbonyl group. The carbonyl group has 2 groups within it. One is an aldehyde. And the other one is a ketone. The next one is an aldehyde. If I had, let's say I have a 3 carbon chain, how do I recognize an aldehyde from a ketone? If this is an aldehyde, if the double bond for oxygen is terminal, it is an aldehyde. If it is non-terminal, then it is ketone. The next group is carboxyl The next group is carboxyl. Carboxyl is, I'm going to have that. That is the functional group, OH. So a good way to think about carboxyl is that it has this double bond as well as an hydroxyl group. The next, let me erase this. How do I erase this? Just to recap, you're going to have this one as OH. This one is COH. But then there are 2 different things. If it is terminal, if the COH is terminal, then it is called aldehyde. And if it is non-terminal, it is a ketone. The carboxylic group is C double bond OH. So it is double bonded with O, and then it has an OH attached to it. An amino group usually, an amino group has an H attached to it. So I might have something like this. NH2. There are different variations of that. Sulfhydryl group has S attached to it. Sometimes it's also called a thiol group. Thiol meaning sulfur. It's called a thiol. The next one is a phosphate group. We will be doing a lot of phosphate groups. It has a polyatomic ion called PO4-3 attached to it. What is a polyatomic ion? In the previous classes, we talked about when molecules are formed, if it's ionic or covalent, the overall charge of that molecule is always going to be neutral. Polyatomic ions are where they have a charge. These guys are covalently bonded to each other. However, they don't form the number of bonds they actually have to form, so their formal charge is either a negative or a positive. And the next one is a methyl group, which is CH3, and it can attach to something there. There's an electron there. It can attach to something there. These are the basic functional groups. You have the basic structure of alkene, alkyne, or alkane, and then the functional groups will attach depending on where the functional groups are attaching to the carbons. So every time you add a functional group, you're substituting it for one hydrogen, one or two hydrogens, however, whichever one you're using. Where it adds itself is going to change how this hydrocarbon reacts. One of the key reasons why we have so many classes of macromolecules and so many classes of organic molecules is because of the functional groups. A 1-hydroxyl is going to function very differently from 2 or 3 or 4 or 7 hydroxyl. Similarly, if it's an iso, which is right in the middle, that's going to function very differently from if it was in the end of it. So each one of these functional groups provide the hydrocarbons a different functionality. How they react with water, what is their pH, how do they react to temperature, what's their boiling point, what's their melting point. Are they hydrogen bond providers or hydrogen bond receivers, and how they react with each other, with one another and its surroundings, ultimately is dependent on the functional groups that are attached. Slide for the functional groups and how they behave. Alcohols usually tend to form polar molecules. All of these, because they have oxygen in them, which has a very high electronegativity, tends to form polar molecules. But alcohols don't have the same number of hydrogen bonds as a water molecule does. Even though both of them are polar covalent, they don't have the same number of hydrogen bonds as water molecules do, so they tend to have a much lower boiling point. In terms of acidity, OH is acidic because when it is dissolved in water, it basically will form this. So it does form H plus ions. In organic compounds, when you see the OH, depending on the context, it's going to either break at the H plus, at the H part, or the whole OH is going to come out. So this one is, all three of them are acidic. Carboxylic is usually called carboxylic acids, and they are much more acidic than anything. So acidity kind of goes in this direction. Hydroxyls are less acidic than carbonyls. Carbonyls are less acidic than carboxyls. Then carboxylic. In terms of acetones and aldehydes, ketones are slightly more acidic than aldehydes because ketones form more resonance structures than aldehydes do. The next group is aminos. Amino acids are more basic than they are acidic. Amino groups are much more are basic. They're not acidic because they become proton acceptors rather than proton donors. In the case of acids, another definition for an acid is that it is a proton donor, because H plus, if you really look at on your periodic table, if you look at hydrogen is 1 and 1.008. It has 1 proton and has 1 electron. It does not have a neutron. So when the electron is removed, if the electron is removed from it, then it becomes an H plus, which is just another way of denoting that it is a proton. All it is a proton. Hence, acids can also be called, because they do release H plus ions, they can also be called proton donors. Bases are OH minus, so they can accept a proton. Amino groups tend to act as proton acceptors. They can go from amino to, they can make an NH3. Amino groups are found in, obviously, proteins, amino acids. They're also found in DNA. They have the NH groups are found in DNA. They're also found in, certain amount of them are found in the phospholipids that you have. There is a nitrogen group there, and some of the additional add-ons that are found in lipids. Sulfur hydryls are very unique to proteins. They tend to form cross bridges. When proteins are made, they're like a really long chain of amino acids, and then they tend to fold onto each other. A very good way to think of it is like if you had a rope, a really long rope, and you wanted to store it, you wouldn't like just keep it stretched out. You'd put it in some place where it'll kind of roll on itself and fall and form either like a spiral, or you can roll it onto something, and they kind of, that is the best way to store it, and you're not going to keep it in a long rope. Similarly with proteins, they tend to fold on themselves and then form because of hydrogen bonds. And if you have two SHs close to each other, so if I had an S which has one and that, and then if I have another S near it, it can form a bond with each other, which is a sulfur, which are cross links or dye bridges, or they're called sulfur dye bridges, which also is plays a huge part in forming the secondary structure of proteins. Phosphates are found in DNA, RNA, all of the nucleic acids. The next one we have is a methyl group. Methyl groups are very, very important in increasing the stability of your long hydrocarbon chains. In the case of, I'm sure everybody has heard of ATCG, which are the 4 nitrogenous bases that DNA has, and RNA has AUCG. The only difference between T and U is the existence of an extra methyl group. T has an extra methyl group. It is opined that it is, there's extensive research to prove that RNA with the U with the extra methyl group actually protects your DNA from being cut by, would have protected bacteriophages, bacteria from bacteriophages. Bacteriophages are just different types of viruses that cut the bacterial DNA. We'll be recapping the functional groups in class on Wednesday. So I'm going to stop right here, and then we'll go over this, or we'll continue this in class on Wednesday. Thank you. I hope you guys have a nice long weekend and have a lot of fun.